Hello, today we're going to be looking at the word problems from Unit 5. And as a matter of fact, as you see that word problem, let's start changing our thinking to call them modeling problems, one of our math practice standards. These problems really are about modeling. They're not about the particular type that they are, but they're more about developing a model. And as we do these problems, I want you to remember that the main goal of this lesson is not to have them be able to solve work problems or to be able to solve shared cost problems, but to practice making sense of problems and persevering in solving them. We're putting this lesson in right here because it gives us a good opportunity to get practice on our rational equation skills, which is something that they still need more practice on, but we can also attack this standard, which is a standard that we are called to teach, having them make sense of problems. There is nowhere in the standard it says they need to have memorized any one certain type of problem, but they do need to be able to make sense of problems. And in fact, the traditional work problem is a problem that is seen in the example problems that you might see on the SBAC. So I would be not at all surprised to see something like that in the testing this spring. So as you're teaching, remember that you want students to make sense of problems. You might be tempted to sort them into types. You might be tempted to give them problems, but formulas. But as you start with them making sense, which means the first thing you should be looking at is not this is a work problem, this is a division problem, this is a that problem, but what are the units here? What do the units tell us we might do with this problem? The units will be a big key for the students to make sense of the problem. They also might be able to just think about the situation and what would they do in this situation? What kind of math would you do to attack this problem? Once they have made sense of the problem, they might find sorting them into types helps them remember which things they figured out about which kinds of problems. And they may eventually develop formulas that you want to recognize and grab onto as simplified ways of attacking the problems. But those formulas should come from understanding the problem and be able to be rebuilt by the students based upon their sense making. And so it's very important to work on what is the problem saying about units, what is the problem saying about the situation, have them make sense of that. So let's just start by looking at a work problem. That's one of the problems on most of the worksheets. You might have different student names because I noticed different leads were changing names to match students in their class, but one of the problems was about washing windows. And Kiana could wash all the windows in a retail store in 6 hours. Maxwell could wash all the windows in the same store in 9 hours. How many hours T would it take them working together? And so some questions you might ask to help them make sense of that problem are, well, how much would Kiana get done in 3 hours? If she could do the whole job in 6 hours, how much is she going to get done in 3 hours? Usually you'll get a half from them on that. How much would she get done in just an hour? Well, 1/6. You're really likely to get at least one live body in the classroom that would know that that would be 1/6 of the job. Took her, if it's dead silent, then my push would be, well, it took her 6 hours to do the whole thing. So in 1 hour, how far done would she be? A half done? Would she be a third done? Hopefully you can get somebody with a sixth. Then how much would she get done in 5 hours? And kids might come up with 5/6 of the job. Ask them how they figured that out. So some of them might have figured it out, well, she's 5 out of the 6 hours done. It's kind of like a ratio. So she would have 5/6 of the job done. They might very likely think of it like that. But other students might think of it like this: 1/6 of the job in 1 hour, and then times 5 hours would give altogether 5/6. Actually, the units should be written like this. That was poor writing on my part. I should be thinking of it more like this. 1/6 job per hour times 5 hours, and then the hours would cancel out, and I would have 5/6 of the job. Okay. So students might think about those units to be able to figure that out, that they're multiplying those two things. And then just have them make a little prediction. If Kiana can do half the job in 3 hours, will it take them together less than, equal to, or greater than 3 hours when they're working together. Hopefully they'll be able to figure out, since Maxwell's a little slower, that it will take them a little bit more time. And so you might just talk to them about that, have them make sense of that problem. That's an important step in being able to go forward in the problems. And a lot of times that's what kids who hold up and just say, I can't do word problems, it's because we rush them through to formulas. I have always rushed them through to formulas, and they don't really understand why the formulas are there, and so they just put up their brakes. I don't understand that, so how can I do it? So give them the time to think about that. Once you've done that, then they should be able to get that Kiana's rate was 1/6 of a job per hour. Maxwell's rate was 1/9 of a job per hour. T was the time worked together, and we're doing that rate times time thing. That'll give you Kiana's work done. The rate times the time will give Maxwell's work done, and then one whole job that will be the total work that's done. And so 1/6 times however much time, whether it's 5 hours or 3 hours, whatever, and 1/9 times however much time. This will give how much Kiana got done, how much Maxwell got done. You add that up, you'll find how much got done altogether, and we know it was one whole job. If that one whole job is a problem, go back to that 5/6. In 5 hours, she got 5/6 of the job. What would she have to know the whole job was done? Well, 6/6 of the job. If she had 6/6 of the job, we'd know it was all done, and that'll give them that one. From here, we get to practice our rational equations work, and I would tell them myself to multiply both sides by 18. Take advantage of the fact that you have an equation. You're allowed to multiply and divide by both sides. On both sides, I'm going to multiply both sides by 18. If I had a slower class, I might actually put that 18 in. 18 over 1, 18 over 1 times 18 over 1 if you want. Make that a 1 over 1 just to keep things really simple, and reduce each one. Show that I'm multiplying each term by 18. So kind of depending upon where your students are at with their comfort. And this solves out really nice. Make sure they put the units at the end. That's part of understanding what they just did, that they did that. Now, I used to give this, it's boxed in red, as an equation that students would just use for this type of problem. Let's look at another one of these, and we'll get back to that equation. They didn't really find that equation, but they came up with it anyway, even though I hadn't told them. So in this other work problem, again, names might be changed, but there was somebody who did 1/20th of the job per minute. Yeshua did 1/30th of the job per minute, and they worked a time together. So 1/20th of the job per minute times t minutes is going to give me t 20ths of a job. That'll be how much of the job Dur got done. 1/20th times t, that's Dur's job. 1/30th times t, that's Yeshua's job, how much they got done. Together, that added up to one whole job. Right here is where we really have meaning. This is nicer to write, and this is a common formula that I always gave my kids before I started worrying about making sure I taught meaning. I would give them this. But where this would fall down for me is if they didn't finish a whole job. What if they got 3/4 of the way done with the job? And my students would write 1 every time. They didn't know what to do when rules changed. And this one comes out to 12 minutes if you want to do it. So students will invent this formula all by yourself if you give them enough time to make sense. And you don't need to have every single student invent it in the class. If the bulk of the class has been able to follow through this reasoning and invent this formula, then letting them use, I'd name it after a kid. We're going to use Josie's formula that she came up with. That was a nice shortcut, right? Here's some formulas you see online, and you might name them. This would be, Josie's formula she came up with, right? Where the time they work together over the Dur's time plus the time they work together over Yeshua's time equals 1. And she says, hey, it always comes out that way. We've done 3 problems, and it always seems like it comes out that way. The time together on the top, their individual times on the bottom, that always equals 1. Another formula I found online was one that looked like this. The time that Dur worked on the bottom, the time that Yeshua worked alone on the bottom, and the time they worked together on the bottom. This one doesn't make very much sense to me. I don't know why it would be like that. I could use it. It wouldn't be that hard to remember, but I wouldn't know why that made sense. You might challenge your kids, why is this the same as this? Why could you use that? And hopefully you can see that if you multiplied through by t, This wouldn't solve anything, but if you multiplied through by t, you would get t over a plus t over b equals t over t, or 1. And so it's the same formula. And so there's lots of possible ways we could arrange this formula. When people understand and make sense of problems, then they choose where they want to leave that formula. As a matter of fact, this was another formula that was on there. If you had two people's individual rates, you could add their rates and make that the coefficient of t. You multiply their rates, make that the denominator, and then put that equal to 1. Well, gosh, that really doesn't make sense to me. It seems like a lot of work. It magically works, but I have no idea why. Again, this one comes from getting a common denominator with this one. If you got a common denominator up here, you would have this. And so you might have been for years, or you might have had a book that taught one of these three formulas, or maybe you have another version of the same formula. And all those are fine, because once you understand a problem, you can stop in whatever step of simplifying it you like. But if you forget it, or the condition changed slightly, these formulas don't always work well for you. If you understand, you can remake them. And so it's important to give our students a chance to make sense. It's, in fact, a standard that we teach our students how to make sense of the problems. It is not crucial that they know how to, these individual problems, but it is crucial that they be able to make sense. And then we're capitalizing on them, giving them a chance to practice their rational function skills along the way. Okay. Here was a different problem. Notice not all the problems were the same type, because we want them to make sense. You only really are sense making on the first 2 or 3 problems that they're doing. After that, they're kind of practicing the things that they've learned. That's good. They need practice. Give them more. But realize that if we want to teach sense making, we have to give different kinds of problems so that they can practice making sense. So on this one, you might remember this. They wanted to watch an event. It cost $72. They were going to evenly divide the cost by this group of friends, and then there were X friends, but then 3 of them decided to go to the movies instead, and then everybody else was going to have to pay $2 more. And so to make sense of this problem, to get to maybe equations, you could ask, if you're one of the original group of people, how would you figure out how much each person owes? And most students have some kind of experience with this, and they would be able to tell you, well, I'm going to take the $72 and I'm going to divide it by however many people there are, and that'll tell me how much I'm going to have to pay, and I can see if I have that money, or if I can afford to bail out and go to the movie for the same amount of money. When the 3 people pulled out, what does that do to the amount each person has to pay? So let them think about that. Like, if 3 people leave, is that going to make me pay more or less? And hopefully they figure out that it's going to make you pay more. And how could you figure that new amount out? So if you think hard about what you did here, you had $72 and you divided among the number of people that we're going to watch. So now we have $72 and we divided among the number of people. Dollars divided by number of people. Taking time to write these kind of little word things down is very helpful for kids, because as you're making sense, ideas kind of flit in and out of your brain. You can almost grab them and then they're gone. So writing down the words of what you're thinking is really an important step for students in this sense making. Dollars divided by number of people. So now there's 3 less people, so that would be X minus 3. And that would be how much the new amount was. And from there, they'll be able to get equations. Cost in dollars divided by number of people ends up being cost per person. Notice how units come from that. The cost in dollars per person is what we're getting there. So here's the initial cost. Here was the adjusted cost. And it said in the problem that the adjusted cost was the original cost plus $2. Each person was going to pay $2 more than their original cost. Again, writing these things down in red is really helpful for the sense-making part. Usually we talk through those and flap them down, or just skip right away to an equation. The kids have no idea what happened, and when they see a new problem, they have no tools to go back to. So writing these things down is really helpful as students make sense of stuff. So the adjusted cost is equal to the original cost plus 2. The adjusted cost is equal to the original cost plus 2. There it is. Then I cleared the fractions and did this. Now, this one got kind of messy as I went, but eventually I factored and was able to get a -9 and 12. 12 really is the only answer that makes sense here. There's probably not -9, even though you might think your friends are kind of negative people. We would not take -9 as an answer. 12 people originally is what we're there, and it went down to only 9. Okay. If you wanted to speak properly, you could say the domain of this function would be positive numbers, greater than 0. Actually, probably greater than 3 because 3 people less went. So there you go. There was another problem kind of like that, like the library, about the library. The library ordered X number of magazines in December, and they spent $80 total on magazines, and that's a fixed cost. It doesn't say it really clearly in there, so you might have to point that out because they have $80 to spend on magazines, and that's all they have. They're not going to just throw in more money later. $80 is what they have. And so they bought X magazines in December. And they talk about average price. So you might want to fish around about how you do figure out the average price. And what that would be is the total money spent on magazines divided by the number of magazines would give you the average price. So the total money they spent is $80. That's a fixed cost. And X was the number of magazines, so this is the average price per magazine in December. Now in January, the average price went up by 70 cents a magazine. And so I said that's the average price in December plus 70 cents a magazine. And here's a question that you might need to ask them. This is a wonderful thing we're teaching them. What do you have to do if you're on a fixed budget and the price per item goes up? If you are on a fixed budget, you have no more dollars, 80 is all you have, and the price per item goes up,